So in this session we are going to introduce this subject of process control, which is another core chemical engineering subject. You see, the process control is very important subject of chemical engineering because here, in order to understand the subject, we need to know all the basic subjects of chemical engineering like fluid mechanics, heat transfer, reaction engineering, mass transfer, etc. Because our objective here is to keep the equipments in sequence of their arrangement at their steady state value. However, see, the processes are connected with each other. So, as a consequence, if any small disturbance occurs in any process device, like something in a pump, a voltage in a pump fluctuates, right. So, the flow rate as the voltage fluctuates, so the torque in the shaft, motor shaft, that will also fluctuate, and the flow rate, because the torque, the shaft is connected to the impeller, so the rotational speed is going to fluctuate, and rotational speed for a centrifugal pump, we know it's proportional to this flow rate, or the flow rate is proportional to the rotational speed. As a consequence, let us say this pump is delivering some feed to a reactor. So, over a certain interval there is a fluctuation in the flow rate, and as the flow rate changes, you know that in this reactor what is going to happen. Definitely there will be a certain fluctuation in the flow rate, and that will affect the conversion. And let us say that from the outlet of this reactor we are feeding that outlet stream to some separator, maybe a distillation column. So, that flow rate will propagate from one device to another device, right. It may be amplified through its course of journey, or it may be actually being damped, right. If the systems are stable, so it will be damped and finally it will die down in this sequence of processes. Otherwise, it may happen that a small fluctuation in any device is going on, it will go on amplifying in the subsequent predecessor device, right, subsequent successor device, right. And these fluctuations will be such that all the devices in the downstream may deviate from their design state, right. This may happen. So, definitely that is a problem in a process industry, and in order to avoid it, we have to fit controllers, right, and there will be some supervisions on that individual controller's performance, right, which will be this main controller which is controlling that specific block, right, and that is the idea of direct digital control. So, we have a block which is giving the individual controllers fitted with that individual process equipments that what is to be done, that means what will be the respective points or the data or the specific desired value at which the outputs of this device are to be maintained, right. So, how these controllers are functioning, what is their principal logic? First we have to understand the configurations of this controller, what are the logic or the philosophy behind this action, right. So, once we have got the basic understanding of the system, that what are the input output relation of a system, how the system behaves, and what are the different types of variables, right, associated to the system in a general configuration, right. It will not be, we will not be looking from this physical origin of the system, like we will not think as it is a distillation column or a reactor or a simple storage tank with inflow and outflow. We will think it is a black box, and what types of inputs are there and what it is generating and what are basically the input and output. Because if we have to go for generating or developing the control configuration, so we have to know that what are the input and output to the black box of that system, and with this input and output how we are going to manipulate this output, right, based on any change in the input, what will be our philosophy, and that will simply replicate in this electronics domain, and finally will design the controller. So, that is the very brief introduction regarding the subject, and definitely we have to think about the stability of that system, that what are the input output relations, and from there how to this implement those control configurations which we are going to discuss. What will be the, how it will affect the stability of these defined processes, and finally the controller design. So that is the overall scope about the subject what we are going to cover here. And so let's start first understanding here that what are the input and output to the device, right. Very simple. We will start with a very simple this process equipment. Let's think it is a storage tank, right. It's a liquid storage tank. We have an inflow. Let's say the inflow rate is Fi, right, and it is an incompressible liquid. And we have an outflow which is F, and in the outflow there is a valve, right, and the level in the tank is H. Now generally what we will consider, that if we consider this as a system, definitely Fi will be the inflow or it is the input, right. F will be considered as an output. Material flow wise, this is the input, this is the output, okay, and H is something related to that specific state of that system. But so conventionally Fi is the input, conventional output variable, and this is some representing some state of that system. But if I am thinking from this idea or the perspective of control, then we have to focus on the device, right. We have to focus on the device, and the state of the device is basically the output of that system, okay. So from this perspective, Fi is definitely from the perspective of control engineering, Fi is definitely the input, right. However, F is also an input. Why? Because we have a valve and we can operate that valve and we can change F. So basically by operating this valve, we are giving an input to that system. It's not, we have to understand that it is not a kind of material flow wise what is the input and output. It's more in a plane of information, what information in terms of input you are giving to the system. So you are giving an information to that system which is Fi, that is the inflow, that this much is the inflow, and as we are able to control this valve, definitely F will be the input to the system. If you remove that valve, F will be the output, right. So as we have a valve and we can operate that valve, we can change F and give an input to the system. F should be considered as an input. So state of the system, the state variables, right. So state variables will be regarded as an output of that system. So H is the output from control perspective, right. So this is an input from the control perspective. So again now there are two different types of input, or two different input rather, Fi and F, right. So if Fi and F, these two are the input, whether there is any characteristic difference between these two, definitely there exists some characteristic difference. What is that? It is basically, if I think of the tank and we don't have any valve here in this line, whatever is in the far upstream, we are not bothered about it. If I focus only in this much of region, right. So here we can see that there is a valve fitted in the output line, but there is no valve in the input line. So Fi is a kind of variable over which we are not having any control, right? So input, they are categorized into two different groups. One is the disturbance, another is the manipulated variable. So disturbance, you see, it's something over which we are not having any control, and that's why we need to control this device. This is the source of a variable. This is a source which will deviate the system from its desired steady state. Say the system is operating in the steady state, Fi has got some value, say it is 50 liter per minute, right? F is also equal to 50 liter per minute, and for that, for this given area, there will be certain value of H, okay, which is the steady state level. Now Fi, because of some disturbance in the pump in the far upstream, Fi shoots up to 60 liter per minute. So there will be a new level achieved by the tank if I am not operating that valve, okay. So the level will be undergoing some kind of dynamics just like this. So H1 was a old steady state at 50 liter per minute, and this is T equal to 0, and H2 is a new steady state, right. So system is adjusting itself, its output, in order to compensate for the increase in the input. So Fi is a kind of variable, input variable, over which we are not having any control, and that's why we call it a disturbance. So Fi is finally a disturbance. And we want to keep H at H1 because that is the desired value. So we will operate that valve, right? We will operate that valve, we will open up this valve such that the level again decreases. So definitely we will not allow the system to reach this H2. So once we see that level is increasing, we will open that valve manually. We were thinking about the manual control, and the level will increase, and then it may decrease below H1, and finally it will settle down to H1 once again. So it may be like this. Right. So this is a controlled process whereas the previous one in blue color, that's an uncontrolled process. Right? But H1 is the desired value of H. So we have to maintain the level at H1 irrespective of the fact that Fi may change. So Fi is changing, right, and it generates the need for the control, right. If Fi is always fixed at 50 liter per minute, there will be no change in H, but that doesn't happen in reality. Fi changes, or there are scopes or reasons for change in Fi. Because the pump in the upstream may malfunction, there may be voltage fluctuation in this motor's armature coil, and because of that its impeller speed will change, which will invariably change this flow rate, and that is Fi. So Fi, let's say there is a voltage surge and Fi increases, right. Fi increases from 50 to 60 over some interval of time, right, and that interval is quite stretched, it may be 10 minutes. So even over 10 minutes, we don't want that level of the tank getting deviated from H1. So you have to keep it H1 at all the time, but it is not possible. Once there is a disturbance, we observe that okay, it's changing, there may be some level gauge or a manual scale fitted side by. So we note that reading. I am trying to operate this manually. I note that reading, and immediately I see that level is increasing. I am not measuring Fi, so I will open this valve. So adjust it, right, based on my experience I will go on adjusting it, and finally the level will settle down again to H1. So this is the idea of control, or the finally here the idea of disturbance and manipulated variable. So disturbance is Fi, manipulated variable is F, and the output, which is also the state variable, and that's also my control objective, which is H. You have to note, and we will give the example, that all the state variables may not be my control objective, but all the state variables are definitely the output. Okay. So if based on this idea that we can have disturbances, we are also having manipulated variable. Without any manipulated variable, it is not possible to control a system. So we must have manipulated variable, and if we don't have any disturbance, definitely from this term of process control, or process control in a typical this chemical plant, there is no need to control the system if there is no disturbance, or the disturbance, once the disturbance, what we suspect as disturbance, is always at its steady state, there is no need to control the device. However, still we can have in some situation, not here, we can have the requirement of controlling it. Just like think, we are processing, this is specifically true in case of batch reactors, and where we are processing some or synthesizing some ceramic materials. And in ceramic materials, what happens? It needs temperature cycles. Like over first 5 hours, the temperature must increase from 30 degree to 600 degree. And we should heat that element or this material at 600 degree for another 3 hours, right. So from 5 hours, from 30 degree, it should shoot up to 500 degree. So the required temperature profile is something like this. So over these 5 hours, this is 5 hour, this is 30 degree, this is 500 degree, and for say here it needs to stay for another 10 hour maybe, and again the temperature must drop linearly over another 3 hours, right, again to 30 degree. So this is the required temperature pattern, what or the temperature state which is necessary for synthesis of that ceramic material. So and we are doing it in a furnace, right, in a typical electrically heated furnace, and there are stabilizers, so there is no scope of voltage fluctuation. So actually there is no disturbance. But the desired state variable, because here the furnace, the primary state variable of interest, which is our control objective as well. There are maybe multiple other state variables as well, but temperature of that furnace is our control objective. And we don't have any disturbance, because we are giving the power to that furnace through a stabilizer. So even if in the main line there is a voltage fluctuation, there will be no voltage fluctuation, we assume, in the heating coil. However, the temperature is to be changed over this following this specific pattern. So we have to control the device, right. So this type of control strategy, this is that control problem where we have the desired value of that variable is progressively changing because of certain special requirement. It's a special type of control, we will discuss it, known as servo control, whereas this one is called regulatory control, right. We will discuss it in detail once we go for understanding the feedback control. So whatever it is, we have to note that there are two different types of input variable. One is disturbance, another is manipulated variable. For in certain cases, we have to measure the disturbance. So disturbances again is classified into two groups. One is measured, another is unmeasured, right. So with that basic idea, now we are able to draw the input output diagram of a system, considering the system as a general one. So that's why it is a typical black box, right? Whatever is happening internal to that system, it's not particularized, it's a general. So we have disturbances. There may be multiple disturbances, some are measured, some are unmeasured. So this is, say, measured, this is unmeasured, and this is the group of input variable we refer as disturbance. And here we will have manipulated variable, MV, right? The system will generate some output, and again the output we are classifying here into two groups, just like disturbance. The some outputs are measured. We'll see here it's only one output and we are measuring it. So there may be multiple other output as well. So these remain unmeasured, right? And mostly we measured those outputs which are my control objective. So here mostly, but that's not the general or universal picture. So this is the measured output, this is unmeasured output. And that is the input output diagram of a system. So with this and very basic understanding, let's now go forward introducing another example, and let's say it's a bit complex one, a binary distillation column. Let's say we are separating pentane from hexane from a binary mixture. The feed is a mixture of pentane and hexane, and we are using a distillation column, multi-stage continuous distillation column, to separate this pentane from hexane. So definitely the pentane rich stream or the distillate will be my top product, and the bottom product will be the hexane rich stream. And first let me draw this, and next we will try to identify what are the input and output, then what are the manipulated variable and disturbances, finally what are the measured input and measured output. So it is F, ZF, TF, temperature, and we are using a total condenser. Here the heat removed in the condenser is Q dot C, and we have a reflux valve. The reflux ratio R is being changed. The distillate composition is XD. The distillate flow rate is D. The bottom product, let's say it's not important, and we are using, or it's not, we don't want hexane, may not be a product. We are simplifying this case hypothetically. The pentane is the product, right? So W XW, right? It's a partial reboiler we are using. And there may be heat loss into the surrounding, Q dot, and the temperature of the surrounding is TS. TS, it is the surrounding temperature. Now I want to keep XD at 95%, or the mole fraction or the mass fraction, let's say it is a mass fraction of this distillate, must be at 0.95 or above, right? But let's say it is 0.95. We are, for the first time, we are not using any inequality. So because this is the requirement for the commercial grade pentane maybe. The product from this device is a commercial grade pentane. Simply we will take the distillate and bottle and sell it to the market. So we have to keep this at 0.95. And we have a feed which is definitely In normal condition it is at the design value, ZF is also at design value, TF it has also got a design value. Okay. Now what are the input to that system? F is definitely an input, ZF is input, TF is input, right? R is input, Q dot C is input, Q dot R is input. All these are input variable because here we have a valve and we can actually control the mass flow rate of the cooling water, and Q dot C you see it is m dot cooling water Cp cooling water into delta TW, right. So as we can change this m dot Cw, so definitely we can actually alter this Q dot C. Cpw and delta Tcw, let us say it is constant, and here also this Q dot R, it's equal to m dot steam into lambda steam. We consider this latent heat exchange, okay. And steam, for steam it is exactly true, the measured heat delivered by the steam is through condensation and that is the respective latent heat. So if I actually change this mass flow rate of the steam, so definitely the Q dot R is going to change. So we are not exclusively writing that these equations are, let us say it is implicit. So without specifying this Q dot C and Q dot R, what they are in terms of this m dot ST and m dot CW, so let us keep it as Q dot C and Q dot R. So definitely Q dot C and Q dot R are manipulated variable, the input, because we are changing it and we are giving this information to that system of distillation column, and as a consequence if I change, see if all these variables are kept constant, I am simply changing Q dot C. So definitely my XD is going to alter, right, or XW will also alter, because as we change this Q dot C, what is the reason? We change this Q dot C, say Q dot C is increased, right, reflux becomes a cold reflux, and for cold reflux, the internal reflux ratio is external reflux ratio plus Cp into delta T divided by lambda. We have studied it in mass transfer. In this chapter of distillation we have studied that. So if I am going to change Q dot C, if I am increasing Q dot C, so if I am increasing this Q dot C, I am actually going to change R because I am going to change the degree of subcooling, right, of this reflux. So with changing delta T, upon changing primarily Q dot C, we are changing the internal reflux ratio without actually operating that valve. Similarly, if I change m dot ST, we are changing Q dot R, so vaporization rate will change. So V bar, so this is finally moving up. So V bar we are changing. So as we change V bar, so we are changing the operating line slope in the strip in section, what we have studied in mass transfer. So as we change the number of the slope of this operating line, definitely we are going to alter this XD as well as XW. Because don't think it from the perspective of design problem. In design problem, as we have mentioned in the other several subjects, in the design problem, the input and output will be given, right, but the device is unknown. Like here the number of stages of this distillation column is unknown and we have to calculate it. So we use either Lewis-Sorel for analytical calculation or Machiavelli under the assumptions of equimolar overflow assumptions and equilibrium stage assumption, and we calculate the number of stages. So that's a design problem. But alternatively, the more difficult one is a simulation problem, where the device is given, your input will be given. Input means these are given, this is given, this is given, and also this is given. And under this condition, we have to calculate what will be my DXD or WXW, the primary output of that system. all are not the control objective, xd is my control objective. So, xd, how it is going to change, right? We have to predict through solving some this mathematics or writing the equations for that system. But that simulation of a distillation column is not within the scope of, or generally we do not study it in conventional understand or conventional this course of mass transfer, right? That is an advanced topic. So, but the thing is, we can qualitatively answer questions of simulation from our understanding of design. What is that? Like we know that if I change the, let us say in a design, what happens if I increase the gap between the operating line and equilibrium line, the number of stages will decrease, right? And that is why in total reflux the number of stages is minimum. When the total reflux means reflux ratio is infinite and the number of stages will be minimum. So, the fact is that if I operate a column with a given number of strains with total reflux, I will reach maximum purity of my product. So, that is an answer to the simulation question from the design, right, from our knowledge of design. But that answer is qualitative. If it is asked that what will be the concentration of the distillate if I operate a column with some specific feed and maybe some 20 number of stages under total reflux condition, and this is Q dot C and Q dot R given. So, under this condition what will be exactly the value of xd, that we are unable to answer because we do not know how to solve simulation problem in undergrad level. The fact is that instead of our inability to answer this value of xd in simulation, we can tell something qualitatively. Like I can say that if I increase the reflux ratio, that definitely the xd is going to increase, right, because the product purity we know it will be maximum under total reflux. So, from this consideration and from this understanding, using certain analogy we can answer the problem of simulation. So, the fact is that if what I am trying to point out, if I increase Q dot R, the V bar is going to increase. So, as V bar increases, the slope decreases, right, because slope of this operating line for the stripping section is L bar by V bar. So, as the slope decreases, you see in the design, this is a 45-degree line. I am not drawing the entire thing. This is the equilibrium line and this is my XW, and that was the operating line initially. So, the slope is L bar by V bar. Now, I am increasing V bar. What will happen? The slope will decrease, right. Slope decreasing means it will be like this. So, the gap between the operating line and the equilibrium line increases. So, the number of stages to reach the given product purity will also decrease. So, that is an understanding, and we can actually quantify that what will be the exact decrease because it is a design problem. Now, with that we can actually say or can propose some statement regarding the qualitative trend of the column with a given number of trays. So, once the column is fixed, the number of trays are all given, the input output everything or input they are fixed, and we are changing only Q dot R, we can conclude that actually the product purity will increase, right. So, this can be considered as one of the input variable because this surely the change of Q dot R is going to alter the performance of that device. So, Q dot R, capital R, Q dot C, F, ZF, TF, they are all input variables to that system. Okay. Now, what are the output? Definitely D, XD and W, XW and TS may be considered as an input. However, this Q dot, the heat loss, is an output. Okay. And there are other numerous output as well. There are few which are of importance. Now, in this group or whatever we have listed as input, what are the disturbances? Definitely we can understand that F, ZF, TF, they are typically the disturbance, because over these variables we don't have any control. So these primarily we will list as disturbance. And definitely R, Q dot C, Q dot R, and TS is also a disturbance. Why? TS is also a disturbance. Because let us say because of this weather change, there is a drop in TS, right. Initially it is 30 degree, right. Now it has dropped to say 25 degree or 26 degree. So the thermal gradient between the thermal gradient between the column and outside, that is going to increase, because TS has dropped, the column temperature, average column temperature is remaining the same. So as a consequence, this Q dot will increase. Q dot is an output. So Q dot, once it is increasing, so definitely for the same flow rate, same temperature, everything, the temperature in the trace of that column is going to decrease. Individually they are going to decrease. So as it decreases, it will alter the equilibrium relation, because vapor liquid equilibrium, we know it depends on temperature heavily. So as the temperature of these trays are changing because of a change in TS, so definitely that will alter the vapor composition and the liquid composition, because equilibrium relation changes. So finally it will affect the distillate composition, right. So TS is another disturbance over which we are not having any control. However, Q dot is the output, right. So Q dot is a kind of output. Finally it affects what? Finally it affects the column temperature. So we can also list the column temperature I equal to 1 to n, all these compositions, right. There are also different other input variables, but they are not of great importance because these are internal to that column. Finally we are interested in XT. So out of all these output variables, mostly everything remained unmeasured. What we are going to measure? Definitely we are going to measure what we want to control, right. So XD is the control objective, because we have to keep this XD at the desired value of 0.95. So this is the control objective, and alternatively this is the measured output, right. Now see, there must be some parity between the number of control objective and the number of manipulated variable. You can't go for multiple numbers of manipulated variable for a simple process like distillation. There must be kind of one-to-one correspondence. Definitely it's not a physical rule of control engineering, it's rather a thumb rule. So for one, unless it is a very complex process, if I have one control objective, we should go for one manipulated variable. Now question is, out of R, Q dot C, Q dot R, these are manipulated variable, of course, because R we can change, Q dot C we can change, Q dot R we can change. So out of these three, which are all manipulated variable, which one is the most effective manipulated variable? So definitely by intuition we can understand that this is R. Why? What is the exact logic, right? See, we have to here think about the dynamics of that system. What is that? If I am going to change Q dot C, how we are going to change? We will change the mass flow rate of cooling water through this cooling coil in the condenser. As a consequence, there will be an increased heat transfer. That heat transfer will change delta T. So that indirectly will change the reflux ratio, and finally the altered reflux ratio will affect XT, right. So it's a staged process. From one stage the effect will propagate to another stage and then to another stage. However, if I directly change R, we can save some time of controlling that column. Like say at time t equal to 0, a manual observer, he identified that XD is decreasing. So definitely what you will do? the philosophy is, okay, let's increase R. So how we can do it? Just by adjusting the valve, or alternatively, I can change the mass flow rate of cooling water in the condenser. But if I do that, if I change the mass flow rate of cooling water in the condenser, and now my objective is to control this XD again to this desired value of 0.95, the pattern will be something like this. Let's say this is the desired value, right. So initially this XD was at its desired value. Now because of certain change in the disturbance, it decreases. So if I adjust R, it will very easily settle down. But if I go on tuning this R, so here this is changing reflux, right. So it will settle again to its desired value over a time interval of T1. However, if I change Q dot C, it may be something like this. So the time required for XD to settle down to its desired value is T2, and T2 is higher than T1, right. So over that interval of T, whatever it is, T1 or T2, we are getting distillate that's not matching strictly with the desired condition. So we have to either recycle it back to the feed tank right here, or we have to simply discard it. So our objective will be to choose a manipulated variable which has the fastest influence on that device. So we will keep X Q dot C as well as Q dot R at their design value, and we will choose R as my manipulated variable because we have only one control objective. So final manipulated variable. Now once we choose R as the manipulated variable, Q dot C and Q dot R should be effectively controlled, and we should maintain it at its design value. Otherwise, if I am unable to maintain Q dot C and Q dot R at their design values, these will be acting as a potent disturbance, right. They will switch to disturbance because everything is running okay, fine, F, ZF, TF all are at design value. Now because of certain malfunctioning, and we have overlooked that, so in the feed water pump to the condenser, there is a voltage fluctuation, or it is malfunctioning, right, or the temperature of the cooling water has increased. So because of everything, this Q dot C is going to decrease, right, Q dot C is going to decrease, and the vapor, whatever the desired temperature of this condensed distillate, we are not achieving it, and that is going to affect the performance of the column and finally the XD. So if I am unable to keep Q dot C and Q dot R at their design value, they are going to be acting as a potent disturbance, okay. So here finally we have to conclude that F, ZF, TF are the disturbances, TS is also a disturbance, R is my manipulated variable, Q dot C, Q dot R are constant parameters in an ideal control paradigm, right. Otherwise, if I am unable to keep this Q dot C and Q dot R at constant at the design value, they will pass into disturbance group. Now there are multiple outputs. Out of those outputs, all these outputs are state variables, right. But out of those outputs, only XD we are trying to control. So this is my control objective, and that's why we are going to measure it. So this is also my measured output. So what is the easiest control strategy or configuration we can implement here? Definitely think manually first. Say we are thinking of possibilities of manual control. So I have to go on measuring this XT continuously, right. So once we get that, okay, it is deviating from the design value, and that is the desired value, which is 0.95, I will go on adjusting the valve. So what if I break it down into steps? What are the steps? First, I have to measure it. right. Next, I have to calculate the error, that is what is the shift of this xd from its desired value. So, it is negative or positive, whatever it is. So, once we have calculated the error, based on that error I will and considering a theory is what? How the distillation column is going to perform, right. So, based on the theory which I have in my mind, I will propose some change in R, right. So, I will propose some change in R. So, there must be an intelligent element whose input will be the output of the measuring instrument, right, measuring instrument. It will internally calculate the error, and based on that error it will generate a signal which is a proposition about to what extent the reflux ratio is to be changed in order to keep this xd or bring back the xd again to its desired value of 0.95. So, it is giving a proposition, right, and that proposition in the signal form will be finally implemented by the reflux valve, right. So, if in a schematic we try to represent through proper instrumentation, what will be the sequence? You see, now I am going to measure xd, and why I am using dotted line? Because it is not a material flow, it is a signal, right. And there are two types of signals what is used in process industry. This dotted line schematically indicates electronic signal, right, and the standard range is 4 to 20 milliampere, okay, 4 to 20 milliampere. For all signals it will be ranging from 4 to 20 milliampere. So, why it is not 0 milliampere? This is a standard that 20 milliampere is the final, but why it is not 0? Why we are starting from some non-zero value? That was a get question. Why we are starting it from the non-zero value? Let us say if the signal is carrying its minimum value, the respective minimum value, then if it is 0, then it is going to give you no signal. But at that time the instrument may be malfunctioning, and we will not be able to differentiate that whether it is malfunctioning or whether it is giving 0 value or 0% value, right. To differentiate that, we keep the lower level at some non-zero value. So, it is 4 milliampere and the range is 4 to 20 milliampere. And the next, in older process industry, when electronic science were not developed, but still we use it in some purpose, we will discuss it. So, if I represent the information flow or the signal flow by this type of schematic or this type of scheme, this is typically representing pneumatic signal, right, with varying air pressure. And what is the pressure? 3 to 15 psig. So, we are first what we are doing? We are measuring it and we are transmitting that signal. So, that, and we are measuring concentration. So, it will be CIT. What is CIT? Or it may be CT as well. It may not be displaying that. CIT stands for concentration indicator and transmitter. Whereas CT, it will not indicate, there will be no LED display unit. It simply transmits the signal, and that is basically we use, right. We do not indicate that in that specific location, we do not need the display. We need the signal to be carried out to the transmitted to the control room, right. So, CT is concentration transmitter. So, remember that in chemical process industry there are 5 state variables which are important. What are they? C, as we have noted, the concentration. T, temperature, F flow, P pressure, and L level, right. So primarily there are 5 variables. So if I am trying to control some temperature, and the respective transmitter will be TT, right. If it is a flow, it is FT. If it is a pressure, it will be PT or PIT if it has got the display option. So CIT is the measuring device. And then it goes to the intelligent element, that is controller. And what it is controlling? Concentration. So CC, concentration controller, right. And concentration controller must know the set point. So we have to give there must be option in this device that we can feed the XD set, which is not the set point, I should say that this is the desired value, which we alternatively refer as set point, right. So this XD set is the desired value of XD, right. Now that will internally calculate the error. And what is error? Error is XD set minus XD. XD what is measuring. So we must give this sort of arrow as well, but the arrow is obvious. This is going to give you the signal, and it's going to give the input to that controller. Controller will generate the decision in the form of a signal, right. So that signal will finally be delivered to the valve. So this valve is a special type of valve, right. It's a special type of valve whose input is an electronic signal, and it is actually changing this flow rate. So this valve we call as pneumatic control valve. We'll discuss about it. So this is our scheme, and that scheme is exhaustively and universally robust. Why it is robust? Because whatever may be the source of disturbance, finally we are measuring the output. So we are measuring the output, and once the output is going to change, we are taking control action, right. So through this measuring device, then the controller, and finally we are implementing the controller's decision through the pneumatic control valve. So information loop, this information of the signal loop, it begins with the measuring device and terminates with the pneumatic control valve. So pneumatic control valve is something where the control loop terminates, or it is the final element in the control loop. So alternatively we call it FCE, final control element. So this FCE stands for final control element, right. So why we are generalizing? Definitely the point is, everywhere the pneumatic control valve may not be a final control element, right. Just like, think in chemical process industry, 90% of the final control elements are pneumatic control valves. But think an alternative process. Say in a room we are using some controller, right, and whenever there is no person working in that room, the lights will dim off, right. The lights will be simply turned off, and this should be done automatically. So how we can do that? We must mount some motion sensors in that room. So motion sensors or some measuring device which will actually identify that whether there is any human present in that room or there is no one. So that is the measuring equivalent to measuring device. The motion sensors or something like that, some equivalent device will be functioning as a measuring device. So that measuring device will give its measured output or measured value to the controller. Now the controller will decide. There is a philosophy. What is the philosophy? Philosophy is if there is no one, then simply switch off all the lights. And if there is someone, then keep the light at its specific luminescence. Okay? So it's simply a typical on-off control, what we have seen in different households as well. Right? So different households, this different kitchen equipments like typical kettle, electric kettle, it's also fitted with an on-off control. Whenever there is a smoke or the vapor at a specific concentration is being issued from a boiling water, then the electric circuit will be switched off, right. So that's also a controller is fitted there. So here the controller's decision in that specific case will be implemented via what? A switch, which is supplying current to the different these lamps and lights or these fluorescent lights, whatever are mounted in that room, right. So there the final control element is a switch, not a pneumatic control valve. Here it is a pneumatic control valve. So what are the other examples of this pneumatic, this final control element? It may be a switch, it may be a relay, right. It may be a solenoid valve, it may be kind of this stepper motor which will rotate at a specific direction, right, by some degree, and specifically that are used in robotics. Okay. Like a robot arm, think that I am trying to replicate the motion of this finger. So here, here and here at these three joints we have three stepper motors and we have to touch something. So what we can do? There will be coordinated movement, synchronized movements of rotations between these three stepper motors. So if it rotates, then this also may rotate, right. But if it is not so complex, say this segment is straight and here we have a stepper motor and the controller gives that, okay, you move by 60 degrees. So it will be moving by 60 degrees. So this is a typical application of control system engineering in robotics. Okay. So there the final control element must be a stepper motor, where here it is the pneumatic control valve. But the philosophy remains same, that we are measuring the control objective or the output of that system, right, and from measuring it we are changing the manipulated variable. So this type of control configuration is called feedback control system, and we will be trying to implement it here in the generalized schematic from that specific example. What we are doing? So these are measured output, right, and let us say all of them are my control objective. All are control objective. So here we go for measuring it. So here we have to measure this current values of the control objective. So there must be a measuring device or multiple measuring device. So output of the measuring device goes to, as we have discussed there in the case of distillation column, it goes to the controller. Now controller must be supplied with the respective set points. Right? Now based on the set point and the output of this measuring device, that current values of this control objective, controller will take certain decision on the degree of the change for manipulated variable, such that we can keep the control objective at their set point, right. So from the controller, the signal will be going to the measuring device, and at each junction we have final control elements. So these dots are final control elements, right, where the controller's decision will be implemented on the physical manipulated variable line. Like there it was a flow rate, right. We are changing the flow rate of this reflux and thereby we are altering the reflux ratio. So It's a kind of control valves, pneumatic control valves in most of the cases. Okay. So, that is the scheme of what is referred as feedback control system or feedback control configuration. Right. So, this one is the most robust control configuration. Robust means whatever may be the source of the disturbance, it will be corrected via feedback control. However, there is a problem in the feedback control. What is that? In feedback control, this XD, if I just simply try to understand its dynamics qualitatively, if there is certain disturbance, it will fall, and then the controllers will be activating the reflux ratio, and it will settle down again to this desired value, right. But over this time interval, we are getting some product that is not satisfying the desired quality. So, that is a waste product over this time interval, whatever we are getting. So, that actually it is a loss. The loss is to be incurred because of this time interval. So, if I want to reduce the time, what we have to do? We have to foresee that, or we have to actually study the performance of this equipment over a long period, a long time interval, and we have to detect that specific disturbance, specific variable of disturbance group which is causing the deviation. Like I have checked the performance of the column, fitting it with the predecessor device, and we have identified that okay, it is the flow rate, right. The flow rate often deviates from its design value, and because of that XD deviates from its set point. So, once we have identified the flow rate as a potent source of disturbance, then instead of measuring this output, now we will measure the flow rate, right, for the sake of composition control. So, we will measure the flow rate and we will check whether it is at design value or whether it has been deviated. So, once it deviates, immediately the controller will suggest that you change the reflux ratio. You change the reflux ratio such that where the change flow rate is affecting the system, its correction is already present, right, because the correction is change reflux ratio and the disturbance is a change in the flow rate. So, they will actually neutralize the effect on XD, neutralize each other, and the effect of this change disturbance will be reduced, and the respective time or the respective dynamics will be something like this. So, here it will settle over T prime, with T prime much lower than T1 if I have properly identified the specific disturbance. So, that strategy is called feed forward control strategy, which we are going to discuss in the next session. Thank you.